Welcome to another exciting episode of Algorithm Analysis and Design. I'm your host and your professor, Dr. John Baugh. This lecture we're going to be discussing sorting, and some of this should be a review to you, and some of it will involve us diving deeper on some other subjects related to sorting. Don't be too afraid from the number of slides. Some of these we will just kind of breeze through, and they won't be too big of a problem because we have talked about a lot of this before. But some of it will be fairly new. So here's our introduction and motivation. So why are we studying more sorting? Well, sorting is a canonical benchmark problem in algorithm analysis. Nearly every real system depends on sorting: databases, search graphics, compilers, etc. It's also a test bed for comparing paradigms. So divide and conquer, we have merge and quick sort, heap and priority queue approaches, and non-comparison sorts like radix and counting sorts. They serve as a bridge to computational complexity and lower bounds. So some objectives: by the end of the lecture, you should be able to compare sorting algorithms by time, space, and stability, derive and interpret the big omega n log n, or the linear logarithmic lower bound for comparison sorts, explain why merge sort and heap sort are asymptotically optimal, describe when non-comparison sorts outperform comparison sorts, and connect sorting performance back to algorithm design paradigms. So where we are in the big picture. So the first three lectures we discussed some algorithmic foundations, and that went to analysis and then divide and conquer. For lectures 4 through 6, we discussed greedy algorithms, backtracking, and branch and bound. And for this lecture, we are basically doing, in many ways, a capstone case study, revisiting the divide and conquer topics, introducing computational complexity limits, and demonstrating paradigm interplay. Sorting as a complexity showcase. So sorting is one of those few problems where both the upper and lower bounds are well understood. We can prove no comparison-based algorithm beats big omega of n log n. Yet by using numeric keys, we can break that limit. So with counting and radix sort, so these are the non-comparison-based algorithms. So that's one major thing to keep in mind is comparison-based algorithm, the limit is n log n. But for others, you can sometimes break that bound. Hence, sorting offers an ideal platform to study algorithm design techniques, asymptotic growths, and empirical trade-offs. Some of the topics we'll discuss: we're going to do a review of merge sort and quick sort, just a brief refresher, computational complexity of sorting, elementary comparisons, advanced comparison sorts. Merge and quick actually kind of fall back under the review, really. But heap sort is introduced. I think we may have made some vague references to that in previous lectures, but we have not really dove as deep. Lower bounds and decision trees, and non-comparison sorts like radix, counting, bucket, and then some comparative analysis on takeaways. So connections to other paradigms. Again, we have divide and conquer. The split and merge of subarrays is how it's related to sorting. An example would be merge sort. Greedy, not directly used typically, but local order choices rarely optimal, and we need an optimality. Dynamic programming, we have bottom-up iterative merges that could be used in iterative merge sort. Backtracking, rare in sorting, no constraints to undo, and then branch and bound theoretical link in some optimization sorts. All right, a little bit of a review for divide and conquer sorting. So a bit of a recap. We break the problem down. We have sub-problems that we solve and then combine the results. It's a recursive top-down structure with divide and conquer. Each sub-problem is approximately half the original input in most cases. And a typical recurrence for the half, it would be b equals 2. We have a times t of n divided by b plus the f of n. That's kind of where the master theorem comes in, right? And some sorting examples would be the merge sort and the quick sort as well. So some notes about terminology we'll use in this lecture are stability and the concept of an in-place sorting algorithm. So stable sort means that the equal key elements preserve their original relative order. So for example, if an element at I is equal to the same element, or an element at j, they're the same thing, and I is less than j, meaning I precedes j, then after sorting, a at I will still precede j. So if it's multi-part, they're objects that have a key. then this is particularly important because if they have the same key, you still want to maintain that relative order. So if it maintains that relative order, that's called a stable sort. In-place sort means that it uses only constant auxiliary space beyond the input array. It's achieved by swapping elements within the same array without having to create a brand full new array. So if we have to do that, we would say it's not in place. All right, some notes. The merge sort array based is stable, but is not in place. It has to use an extra temporary array. The linked version of the merge sort is both stable and in place. You just have to move pointers themselves. Quicksort is not stable, but is in place and swaps elements in place. Heap sort is not stable, but is also in place. So you have to maintain something called a heap structure, which we'll talk about. All right, back to merge sort real quick. This is most of this is just kind of copied from a previous lecture, so we're just going to kind of breeze through this. But remember, the key idea is we split the list into two halves, recursively sort each half, merge the two sorted halves, right? It looks like we got two of the exact same slides, so I'm going to fix that. All right. So here we go. So input, you have an array of size n, and when you divide it, it splits into two halves. Size of the n divided by 2 floor and the ceiling of n divided by 2. You recursively sort each half and then merge the two sorted halves into a fully sorted array. Sorting is done after reaching arrays of size 1, if you use the pure merge sort technique. Now, in practice, we usually, once you get down to a certain number, maybe size 8 or size 16 or even 32, depending on the implementation, we typically just run a quick insertion sort on it. So here's the visual showing what's going on. So you split it, just like we did in the previous lecture. We split them into smaller arrays until you get to size 2, technically size 1, but I'm showing it now that you're just swapping them right here. And then you get these small subarrays that are themselves sorted, and then you shuffle them back into place. You'll notice that some of them may not end up exactly size 2 in this case, or size 4 in the next case. But they're most of them in general are going to be a power of 2. Okay, there's some pseudocode. Won't bore you with that. There's some real code. The recurrence relation, the master theorem, obviously look over those just to review them. But here's an improvement. This is something we did not really discuss before. The improvement, an iterative bottom-up improvement, is the key idea is you start with one element runs, then iteratively merge adjacent runs. Each pass doubles the run size, so 1 to 2 to 4 to 8, etc., all the way up to n, and eliminates recursion and stack overhead. So you can use an iterative approach. It's the same n log n time, but often better cache performance. Okay, so for example, if I had, I start considering the full array, I look at the full array, but I consider it as just all separate subarrays. So in this case, 7 separate subarrays, 3, 1, 4, 1, 5, 9, 9, 2. You merge the pairs of size 2. Like I'd merge maybe a 3 and a 1, then I get 1, 3 because that's how you merge them. So you're basically starting as if they were all started split. Okay, kind of like we had the tree up here, but you're just starting from this spot where we're doing the merge, really is what you're doing. And you're considering it, 38 and 27, well, the 27 goes first, the 3 and the 43, so you skip the split stage, really. It just kind of naturally happens. So it's similar in spirit to a dynamic programming approach to the same problem. So here's our example. Treat the elements as a sorted run. So each element individually is trivially sorted within its own subarray. Then you merge the adjacent pairs. So you get 2738, 343, 982, and 10. With pass 2, you get you shuffle them back in, so you get the 3 is the lowest, then a 27, then a 38, then a 43. And then the other one is 9, 10, and 82. And then pass 3, the final pass with size 4. Each of these is size up to 4, really. You shuffle them into place, and you end up with the fully sorted merged array. And here's just an example of the code. What you're doing to do the iterative merge sort, finding the length, setting the size to 1. Well, in as less as that size, we loop through and go in the range of the those elements, calculate the midpoint, calculate the right part, and then do a merge. And we assume we have the code for merge already. A linked implementation, the motivation for linked implementation would be Large records are expensive to move in memory. So we add a link field and merge by pointer manipulation rather than by copying records. The advantages are that this drastically reduces input-output for large or disk-based data sets and preserves the stability. So it's common in file systems and database sorters. Performance is, again, time as n log n, and the space is just big O of n. Practical enhancements. We mentioned some of this, I think, but you've got small run optimization. So switch to insertion sort. I mentioned that earlier for subarrays below a small threshold. For example, less than or equal to 32 or less than or equal to 8 or what have you. You just quickly run an insertion sort. So in practice, it typically does better than if you use pure merge sort. There's natural merge sort, detect existing sorted subsequences, and merge only where needed. So this is used in a technique called Tim sort. Parallel merge sort, both halves can be sorted concurrently. All right, a little bit of an example with quick sort now. So we move on to quick sort. This is, again, what we did before. There's the divide partition based on the pivot. A conquer is the recursively sorting the left and right subhalves, also using quicksort, and then combine. Okay, I'm not going to go through this. Just remember some of the highlights. Median of 3. Constant time selection gives a guarantee that you're at least not picking the worst value. It could be the second to worst, but it's not the worst. On average, tends to perform quite well. Okay, then there was an example given right here. So I, again, won't go through the whole thing. Some of this kind of, I think, changed because I did copy this from a previous lecture, so this might be a little bit oogly. Might try to change that a little bit later, but you can at least see what's going on. You've got first, mid, there we go, first, mid, and last, first, mid, and last, and you can see that it's treating it like different, you can keep visualizing it as treating these elements as passing one another and getting the, not the elements rather, but the pointers here, or the I and the J that are the arrows pointing up, eventually will pass one another, and then you'll put one of the elements in the right place, the pivot, and then you know that the lower half is smaller than it, the upper half is bigger than it, and it works pretty well like that. So in practice, quicksort tends to be the fastest of all those sorting algorithms. I won't go through these again because we did actually do this lecture too, but I do recommend strongly you go over this again just to prepare for tests, interviews, things like that. There's our quicksort sort, our recurrence relation with master theorem. As a performance summary, best case, n log n, assignments n log n, space log of n, balanced partitions, on average, 1.39 n log n. It's got log of n space, random with a random pivot. Worst case is the pivot ends up being the minimum or the maximum. Then it actually ends up degrading to n squared over 2 instead of a logarithmic. So basically, quicksort becomes a crappy version of just insertion sort if the pivot is picked poorly. So for example, if the array or the data structure that's passed into the quicksort algorithm is already sorted, it's going to keep picking, say, the first or the last element. That would be the kind of the min-max, or ends up doing the min-max because you're picking first or last element. It's going to always pick, like, say, for example, if it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it's going to pick the 10. So then, hey, that's my pivot, yay. But the problem is yes, the 10 is going to end up in the correct space because it's already there. But what about all the stuff that's, greater than it? Well, there isn't. Everything's going to be on the one side. So you didn't really improve. And then the same thing with the next one, the next one, the next one, etc. So you never really get to divide and conquer. Tail recursion is one of the optimizations that can be performed on quicksort. So after partitioning, only one recursive call is required. Always recurse on the smaller partition. We loop on the larger one. Keep recursion depth less than or equal to log of n versus a potential n. And then the same n log n, or linear logarithmic, whichever you prefer. Average runtime, drastically lower stack use. So, and then here's some code based on how to do the tail recursion optimization. There are some hybrid variants that you should be aware of. Again, kind of like merge sort, we switch to an insertion sort for small partitions, less than or equal to 10 or 32 or something like that. Randomized pivoting, that guards against adversarial inputs. Intro sort is used by C++ standard template library. Starts as quick sort, and then if the recursion depth is greater than 2 log n, once you get to that point, you switch to heap sort. So that actually guarantees n log n worst case. Some stability and use case ideas here. You've got quicksort is not stable, meaning equal elements can swap. Excellent for in-memory array sorting with limited space. Merge sort is preferred for linked records or when stability matters, so that's a use case of it. You would not use quicksort typically for linked records or stability. Heap sort is a safe fallback for deterministic linear arithmetic but slower constants. More on heap sort in just a bit. So computational complexity of sorting. Sorting is one of the few problems with tight asymptotic bounds. So for comparison-based sorting, the upper bound, merge, heap, and quick, all have big theta of n log n. Okay, so they're all linear logarithmic. Lower bound is the omega of n log n. It's provable via decision trees. The question is, can we ever do better than big theta of n log n? And the answer is not if you use comparison-based sorts, but you can if you use non-comparison sorts, and that's coming later. Okay, it looks like we also got another duplicate. I do a lot of copy-paste of slides because it keeps the format right, so I sometimes accidentally include them and forget to take them out. So a decision tree model, we haven't really seen a decision tree model yet. We've seen various trees in various forms, but this one is a special form that we look at where each comparison between two elements can be represented as a branch. So this is a visual for it, basically. Each path corresponds to one possible sequence of outputs, and a decision tree for n elements has at least n factorial leaves. Okay, so one per permutation. The minimum possible height is log of n factorial, or log base 2 of n factorial. Therefore, any comparison-based sort requires big omega of log base 2 of n factorial, which is actually approximately big omega of n log n, number of comparisons. Here's an example. Let's say if we're trying to, for example, sort 3 elements, so A, C, B, A, B, and C, we're trying to sort them depending on their values. The question here means we're asking the question, is A greater than or less than, or how does that work? Now, if they're, we probably should include like an equal as well on these. So I think we'll probably maybe do that, but I'll just leave it for now. So is A less than or equal to B? We'll assume that they're distinct for this example, but we could make one of them greater than or less than. So is A less than B or greater than B? Well, if it's greater than B, we go over here. Okay, so that's basically said that A, so if A is over here, we then ask the question, is A greater than or less than C? Okay, and then you ask, is B greater than or less than C? Okay, so we assume that in this particular instance, the larger values are actually going towards the end. So you can see, though, if A is less than C, but it was greater than B, this makes sense because A is less than C, which is at the end, that's the largest value, and B is less than the A. All right. Now, what about over here? So if you go down here, you get is A less than or greater than B? Let's say it's less than, then we would go here. Then we have to make another decision. Is B less than or greater than C? If it's less than, we end up with ABC because that's the order that we would get this way. If it's greater, we do one more comparison, A compared to C. And then if A is greater than C, then it ends up in the second place. If it's less than C, then it ends up in the first place. So how do we even derive the big omega of n log n bound? Okay, so mathematical steps are recognize the number of possible input orderings. It's n factorial. Okay, that's the possible orderings of that A, B, and C, for example. Okay, you could have A, B, C, A, C, B, B, A, C, B, C, A, right? You could have C, A, B, C, B, A. Okay, it's all the permutations. And observe that each comparison can yield 2 possible outcomes. This should actually be at the next one. For correctness, 2 to the power h is greater than or equal to n factorial. Therefore, a decision tree of height h can have at most 2 to the h leaves. Require the tree to represent all possible orderings for the algorithm to correctly sort in every case. That's 2 to the h greater than or equal to n factorial. And take the logarithm of both sides to isolate h. Okay, so h greater than or equal to log base 2 of n factorial is approximately n log base 2 of n, and then minus the 1.44n plus big O of log of n. So we conclude the fastest growing part of this isn't the linear or logarithmic terms, it's the linear logarithmic term right here, linear arithmic. So that's why we end up with n log n. So what are the implications? No comparison-based algorithm can be asymptotically faster than big theta of n log n. Merge sort, heap sort, and average quicksort meet that bound. So they are when they are asymptotically optimal. Insertion, selection, and bubble sort, what we would call the say the fundamental or elementary sorts, those are all quadratic. Okay, so they have big theta of n squared. So they're suboptimal. So you can be suboptimal. You could make a terrible sort if you want to even, and be worse than quadratic. But you can't get better than linear logarithmic, unless you do something special. So the only way to do it is to not use a comparison-based sort. Is there another way to sort them without actually comparing the two values to one another? And the escape hatch, quote unquote, out of this is to use a key structure, the key structure, instead of the values themselves. So counting, radix, and bucket sort use that key structure. Okay, in practice, merge sort has a consistent linear arithmic complexity and it's stable. Heap sort has a deterministic linear arithmic linear arithmic complexity and it's in place. Quick sort has an n log n average, and it's faster than the other linear arithmic sorting algorithms in practice when it is implemented properly with a good pivot selection protocol. Optimal asymptotic case is n log n, but constants and stability differ in practice. Okay. Let's start on elementary comparison sorts. Alrighty, so the elementary comparison sorts that exist are typically simple, relatively intuitive algorithms like selection sort, insertion sort, bubble sort, which I also call lazy student sort, and shell sort. So generally they're quadratic time, except shell sort, which has an improved average performance. They're useful for small data sets or as building blocks for hybrid algorithms. Foundation for understanding more efficient sorts. And as a side note, bubble sort, this was Dr. Bruce Ellenbogen. Very few of you probably know him now, but he was one of my mentors, and I taught with him on a couple occasions, had him as an instructor myself, and he was on my doctoral committee and all sorts of things. And unfortunately had an aneurysm in 2018 and passed away while on vacation in Hawaii. So that was an unfortunate and sad time, but he produced this alternative name since bubble sort is easy to implement, but is terribly inefficient. So he called it lazy student sort. So I'm continuing that tradition. So selection sort. Key idea with selection sort is that we repeatedly find the smallest remaining element or the largest, okay, and move it to its final position. So with smallest, if you want it in ascending order, you would move it to the front. If it's largest and you want it in ascending order, you move it to the back, okay? So basically find the next minimum or maximum in the remaining unsorted values and then put it in the correct place. Steps are for I from 0 up to n minus 2. We find the smallest elements in the A from I up to n minus 1. Swap it with A at I. The reason it's the n minus 2 is because we go up to n minus 1 And then we want to swap it with the A at I. Okay, so at the very, very end, we're going to have that kind of gap at the end. So we want to make sure that we do it properly, because the last one, by definition, would be in the correct position. Repeat until the array is sorted. So number of comparisons are n times n minus 1 over 2. That gives us a big theta of n squared. Okay, and again, you'll see equals a lot with a lot of these, but I typically would use the is element of symbol. I would probably prefer that. I don't have it on there, so but we would typically prefer that. But it does mean it is part of that. It's not equal to a single value. You have to keep that in mind. Number of swaps is n minus 1. It is in place. It is not stable, though, because swaps may change equal element order. And you might think, well, why does that matter? If we have 2 3s, we've talked about this before, but in the previous stuff, but why does stability matter? If we have 2 3s, why does it matter if the 1 3 goes before the second 3? Well, it isn't so much when it's primitive data like that. It's that if that's a key for a larger piece of data. Okay, that large piece of data might be a person's record, or an individual, maybe in enemy data for a video game, or all kinds of stuff. And if you sort them and you find 2 things with the same key, whatever the key is that you're sorting by, it could swap the entire or pointer or reference to those objects or the objects themselves and put them in a different order than they were prior to the sorting. Okay, so if they have the same keys, this does not guarantee that the one that was before the other one will still be before that other one. Okay, it's best used for small arrays where swaps are costly, so it minimizes the movement. Example of selection sort, if we have 5, 2, 8, and 4, the first pass, what I would do is I would find the smallest in the entire thing, okay? That would be the 2, and I'd move that to the front. I'd swap it with the one that it's coming from, and the one that currently occupies the position it wants. So the 2 and the 5 swap. So now you have 2, 5, 8, 4. Find the next smallest. The next one's a 4. And I want it to be there, so I have to swap it with the thing currently in its position, so the 4 and the 5 switch. So now you have 2, 4, 8, 5. And now these two are definitely sorted. So now we look at the 5 and the remaining 8. 5's already smaller than 8. The 8 and the 5 is what we had before. The 8 is larger than the 5. 5 is smaller than the 8, so we swap them. And then we end up with the sorted array 2, 4, 5, 8. The next one is insertion sort. This one is kind of like if someone is playing poker, if you're familiar with poker, or any card game, and you know how to organize the cards in your hands. A lot of people do it while they're playing. They'll put, say, the 2s together, deuces together, and the aces together, or put it in, if it's a straight or something, you've got the A, 2, 3, 4, 5, so you put it in some sort of order. So it's basically you start with something that you have that's sorted, maybe 3 cards are sorted, and the dealer gives you another card, and you pick up that card, look at it, and put it into the right place. In other words, you insert it into an already sorted collection, okay? So you build the sorted portion one element at a time by inserting each new element, into its proper position. So this one is not looking for the next maximum or minimum, it's looking at the next element and then just putting it into the correct spot. So the steps are, we start with the second element, compare backwards with already sorted elements, shift the larger elements 1 position to the right, and then insert the current element in the correct place. It's big O of n in best case if it's already nearly sorted. We don't do really many swaps, but the average and worst case are n squared. It's in place and it's stable. It's excellent for small arrays or as a subroutine in hybrid algorithms. So when we talked about, for example, the Tim sort with merge or the quick sort, once you get down to a certain size, you just run insertion sort on it. That's because it's very efficient when it's a very, very small set. Okay, so here, this vertical bar here is not a mistake. That's there to represent the things to the left of it are sorted. The things to the right are not considered sorted. So in this case, nothing's sorted yet. There's nothing to its left. So we first move it over to the right one, and then you kind of treat them like they're 2 separate arrays, even though physically you would not do that. You're treating it logically like it's 2 separate arrays. So you've got an 8 on the left, which is trivially sorted. It is sorted because there's only one element, and to the right is unsorted. The next thing you do is you compare the 4 with the 8, because we want to move over once, right? So you have the 4 and the 8. And what do we do with that? Well, the 4 actually should be put in front of the 8. So you do that and then shift the bar, which is, this is logical. It's also not there in practice. It would be there basically created by an index or something like that. So you end up with 4, 8 on the left side. So that is definitely sorted. We maintain it sorted. Think of it as the card analogy, right? You just got 2 cards, a 4 and an 8. You put the 4 and then the 8 right after it, and now you're ready for the next card. When you see a 6, you see, well, the 8's too big, so I put it to the left. Now it's bigger than the 4, so I put that between the 2. So you end up with 4, 6, 8. Shift the bar over. So I've got the sorted side is growing, the unsorted side is shrinking. And now I ask, what do I do with the 2? Okay, well, the 2, compare it with the 8. I shift 8 to the right, make room. Shift 6 to the right, make room, because the 2 is still smaller. Shift 4 to the right and make room, and then 2 goes at the beginning. And then at the end of this, we've got nothing unsorted. The whole thing is sorted, so it's 2, 4, 6, 8. Who do we appreciate? Dr. Baugh. That's right. All right. Next one is bubble sort. This is the lazy student sort. You repeatedly bubble up the largest unsorted element by swapping adjacent out-of-order pairs. Okay. Steps are, for each pass through the array, you compare A at J to A at J plus 1, the one after it. And then if A at J is greater than its nearest neighbor, you swap it. The comparisons are n squared. The swaps are n squared also. That's what makes it inefficient. Stable, and it's in place. So these two are good, but the reason it just keeps swapping. As long as the thing, it basically bubbles up from where its position is up to where it needs to be. And if it's, instead of just doing a bunch of comparisons and finding where it goes, it just keeps moving. So there's a lot of swaps going on, and that's not very efficient. So here's 5, 3, 8, 4. Compare the 5 and the 3. Well, the 3 should be less, so the 3 goes there. The 5 is here now. Now compare the 5 and the 8. No swap. Compare the 8 and the 4. 4 and 8 swap. So we did a couple swaps there. Pass 2. Compare the 3 and the 5. No swap. Compare. We're doing a lot of re-comparisons also. So no swap there. But then we do the 5 and the 4. So we swap those, and then next largest element 5 is already in the correct position. Pass 3, compare the 3 and the 4, no swap, etc., etc., and then you find that there's no other swaps to do. You go through the whole thing and find out it's already sorted, so it's good. Shell sort. This one's kind of a bridge between the elementary and the more complex advanced sorts. So it improves insertion sort by allowing initial comparisons across a gap. Okay, this is called H sorting. As the gaps shrink, the list becomes partially sorted, reducing the total moves. The steps are choose a gap sequence, so 2, 4, 1, etc., and then perform insertion sort within each gap. So continue until the gap equals 1, and then the final pass sorts completely. So the analysis is, in worst case, you get n squared, and n to the power 1.5, or 3 divided by 2, depending on the gaps. So on average, though, you get, that should be n log n. That needs to be... one second. There you go. Yeah. N log base 2 of n. Okay, with good sequences. It's not stable, but it is in place. It was invented by David Shell in 1959 and conceptually bridges some of the simple and the advanced sorts. So 8, 5, 3, 7, 6, 2, 4, 1. If the gap is 4, we start with the gap of 4. Compare elements 4 apart. So we've got the 8 compared with the 6, because that's 1, 2, 3, 4, right? And then the 5 and the 4, 5, 1, 2, 3, 4, I'm sorry, 2, 5 and 2. And then 3, 1, 2, 3, 4, 3 and the 4. So you've got basically these groups that you're considering. And then each group is sorted using insertion logic, okay? So we move the 6 over to this side, and the 8 moves over to this side, because remember we've got the size 4 gaps. And then the 5 and the 2 goes to the front, the 5 goes to the right side. 3 and 4, they remain where they are. The 1 and the 7, or 7 and 1, the 7 goes to the right, the 1 goes to the left, so that makes it a partial sort. Then you make the gap of 2. You compare and sort pairs that are 2 apart. So you have the indices of the things we're comparing are in the different element lists are 0, 2, 4, 6 and 1, 3, 5, 7 because the gap is 2, right? So 6, 1, 2, that's a 3, 1, 2, that's an 8, 1, 2, that's a 4. Okay, that's why we have 6, 3, 8, 4. And then starting at 2, 2, 3, 1, 8, 5, 4, 7. So that's why we have 2, 1, 5, 7 there. So you treat these as 2 separate groupings, right? 6, 3, 8, 4. And you basically do an insertion sort within each group, okay? So here you get 3, 4, 6, 8. And then the other one you have 1, 2, 5, 7. So you end up with a new array, 3, 1, 4, 2, 6, 5, 8, 7. Now notice that these are within their group. So 3 and 1 go back into their positions. 4 and 2 go back into their positions. 6 and 5 go back into these positions. And then 8 and 7 go back into the remaining positions there. Okay? So the next thing you're going to do is you're going to... Oops. Oh, I think I skipped over a bunch of stuff. It's insertion sort, bubble sort, shell sort. Okay, yeah. So the next thing you do is a gap 1. Okay, so this one just really, this boils down to a normal insertion sort at this point. But the idea is that most of the stuff will be in better order than they were before. Okay, so not as many swaps, hopefully. So 3 and 1, you get 1 and 3, add the 4 in, already in place. 2 goes down a couple. 6 is already in place. 5 just goes down a couple. 8 or 6 goes in its place. 8 goes down 1, and then 7 goes down a couple, and you end up with 1, 2, 3, 4, 5, 6, 7, 8. All right, and here's just a comparison chart. Not going to go through the whole thing, but you can see whether they're stable or in place, what their worst case, average, and best are, and then some notes on them. Okay, so advanced comparison sorts are really where we want to kind of park out. These algorithms reach the theoretical lower bound for comparison-based sorting. So each takes a different approach to achieve the big theta of n log n, or the linear arithmetic bound. You have merge sort, which is divide and conquer. Quick sort is divide and conquer with partitioning. And then selection-based, or heap sort is selection-based with priority queue operations. Okay. All right. So this is just another comparative overview. We did look at similar diagram a little bit earlier, but you can see the merge sort, quick sort, heap sort, and then some of the summarization of stabilization and in-placedness, and then some notes based on those as well. Okay, so since we already worked on merge sort and quick sort, let's kind of focus on heap sort. So this is newer to us. The idea is that we'll use a binary heap to repeatedly extract the largest or smallest, depending on what kind it is. If it's a max heap, then we always keep the largest value at the top, and each value at a node is larger than both of its children. So this is a binary heap is different from a binary tree, or a binary search tree. Rather, it is a binary tree, but it's a binary heap rather than a binary search tree or BST. A binary search tree would have your left child smaller than you, your right child greater than you is typically how it's organized. With a binary heap, if it's a max heap, you are always greater than both of your children. And there's not really a rhyme or reason necessarily to which one goes on which side. Let's say you're a 10 and your children are 7 and a 2. It will kind of just be luck of the draw with how they were inserted, whether the 2 or the 7 are on one side or the other. Now, if you go down on that tree, it has to maintain a structural property and a heap order property, which we'll talk about in a minute. But the algorithm steps are build a heap from the array, that's a linear operation, repeatedly remove the root, either remove max or remove min, and rebuild the heap. So rebuilding the heap is kind of the heap up, heap down type operations. Collect elements in reverse order, sorted array. Each deletion acts like selection sorts find max step, but the heap makes it big O of log of n instead of big O of n. Okay, first let's build a max heap. We add the items one at a time, maintain 2 different properties, the structural property complete tree, and then the heap order property means each node is larger than both of its children. That's supposed to be in there. Sorry. So the starting values 13, 2, 9, 15, 21, 7, and 18. So very beginning, we add the 13 to the tree. So there's not really much to do here. The structural property means that it has to be a complete tree. It means it's filled in from left to right. Okay, you're not going to have any right children with no left children. And it goes down, right? So it's filled in like that. Now the heap order property is also maintained because since it's only one node, it's obviously larger than its children, which are non-existent. Now we add a 2, okay? First, you always concern yourself with the structural property. You want to make sure that it remains an actual complete tree before you worry about the heap order. So the complete tree says we have to fill in from left to right, top to bottom, left to right, rather. So I always add to the next position, then worry about the heap order. So I add a 2 to this position right here as the left child because we're filling in from left to right. Okay, I don't add it to the right because then there would be an open spot on the left. I have to fill in from the left to the right at each level. So if I go down another level, I do the same thing. I would go to the left child, right child, right child, and then down, etc. So I have 13 and 2. The structural property is maintained. It is a complete tree, but I ask the question, does it maintain the heap order? And the heap order tells us is each from adding that new one, is it in the correct position relative to its parent? And since it's a max heap, that means that the larger value is the parent. So 13 is bigger than 2, so we don't need to make any modifications. The next thing we do is add a 9. Okay, so that fills in the position that it needs to, which is filled from left to right. Okay, and this will have filled this level. Just like with 13, the one node filled that level. These 2 nodes fill this level. So that means the next move I'm going to have to start down at children of 2 because I'll go from left to right. And there will be 4 children total possible in there. Now, I added the 9. It is structurally correct. Okay, it is a complete tree. But I asked the question, does it violate the heap order property? The answer is no. It does maintain the heap order property because 9 is still smaller than its parent, 13. Next thing we do is add a 15. Again, structural property. The 2 and the 9 are filled up at this level, so I start on the next level. You fill in from left to right. So 15 goes there as the left child of the 2. So the structural property is fine. It's maintained. But the heap order property is violated because you asked, is 15 less than or greater than its parent? And the answer is that it's actually supposed to be larger than in the way it is now, it's it's larger than its parent, and we can't have that. So we have to swap those. So that's a heap up operation. That's restoring the heap order property. So 15 goes up. So now for this subtree, the heap order is preserved. Remember, they're structurally recursive, so we ask in terms of subtrees. It's not going to affect the right side at all, really, but we're concerned about this left side. So 15 and 2 are in the correct order now. Now you ask, is 15, since it has a parent, you only stop when you're either at the root or your parent is larger than you. Compare the 15 to the 13. What happens? Well, the 15 is actually greater than the 13 also, so you have to swap those values. Now we're back in business. Okay, now we have not only the structural property, which was maintained from the beginning, because we have that as a first order consideration, but the heap order is restored now. Okay. Now, next thing, I kind of grade these out so we can keep track of where we are. I've already added those. I want to add a 21. So you add the 21, and we go structurally. So 15, we go down to the left because there's positions ready here, and we want to go to the right child of the 13, and we add our 21 there. So structurally, it's good. We're good. It's a complete tree. Heap order property, not so good. So I look at my parent and say, I'm larger than them, so you swap with them. So now 21 is now in that parent position. The value 13 goes down. Now you compare 21 with its parent, 15, and you say, wait a minute, you're in the wrong place. That's my spot. And then the 15 and the 21 swap, and now the heap order is restored. So 15 used to be the largest number. It used to be the root. It goes down to the left to swap with where the 21 was, and now we have the value. Okay? So now you go, or the large value at the top. So you can see it at any level, each value is larger than both of its children. So 21 is larger than the 15 and the 9. 15 is larger than the 2 and the 13. What do I do with the 7? I add the 7 structurally over here as the left child of the 9. You'll notice that that is fine. It doesn't violate anything because it's already in the right position, and it, of course, maintains structure because we put it there. I've grayed out the stuff I haven't worked with yet. So what about the 18? Add the 18 as a right child of 9. And then what happens? There's a heap order violation. So I swap the 18 and the 9, put the 18 there. I compared that with my parent now, the 21, and 18 is smaller than 21, so it's in the correct place now. So this is our whole tree here, representing this heap. Now, to actually perform the sort after we've created the data structure, so it's basically kind of a big O of n type move to create the data structure, we now want to call remove max repeatedly until all the nodes are gone. And we are going to continue to maintain the structural and the heap order property. So removals with a heap, which is what this thing is called, have to maintain the structural and the heap order property just like insertions do. So to remove elements, it's easiest to remove the element at the bottom. Now, if we look structurally, what's the easiest node to remove? The easiest node to remove is the 9 over here, the node with the 9 in it. So now we're thinking about the actual node, not just the value. But I don't want to lose that value 9 because it's not the one that's supposed to be removed, right? It's supposed to be the 21. So the easiest thing to do would not be to delete the node at the top and then try to figure out, well, wait a minute, which of your children's bigger? Oh, move the 18 up, and then what happens to the 7? Wait a minute, it has to have a left child, so move it down to the right or the left, and it just gets confusing. So the easiest thing you can do is just swap that 9 and the 21 right here, and then now the heap order is violated because the 9 can't be at the top, but we've got a really good thing to maintain the structural property, don't we? Because we can just remove that 21, that entire node now. So this is our tree, okay? And we put it in our sorted array. So here's our array that we're keeping track of. There's the 21. Now what about here? Now we have to restore the heap order. So the 9 doesn't belong there. Now in this case, you do swap with your larger the larger of your children. Why do you do that? Because if I swapped with the 15 right now, what would happen? It would just reviolate the heap order property because 18 would be larger than it. We'd have to do it again. So it's just better to always swap with the larger of your two children until you are in the correct place. So that's what we do. So the 18 and the 9 swap. This is not affecting the array that's being sorted. It's just restoring the tree to what it should be. And then you'll notice that 9 is greater than 7, which is its child, so it's in the correct position now. Now we want to call remove max again. We remove the 18, and then do the swap, right? So we want to remove 18, we do the swap, and then remove that node. 7's at the top. We add that 18 to the sorted array, but we have to reheap or heap down that 7. So what do I do? Which one do I swap with, the 15 or the 9? And the answer is the larger of the two. So I'm swapping with the 15. 15 goes to the top, 7 goes down there. Now, is it still wrong or is it good now? Okay, is the 7 larger than both of its children or greater than or equal to both of its children? The answer is no. Even though it's bigger than the 2, the 13 should be higher than it. So we swap with that one. And now we've restored the heap order. So this is now a heap again. It's a good, wonderful working heap. Now we call remove max again. It adds the 15 to our sorted array. And you do the swap, the 15 and the... sorry, wait a minute. The 15 and the... oh, that already got moved up. Sorry, the 13. So we remove max, remove the 15. 15 gets swapped with that 7, and that node gets removed. The 7 goes down. Okay, swaps with its larger child. Okay, skipping some steps now. So the 7 swaps with the 13. So now the 7 goes here, the 2 is there, and then the 13's at the top where it belongs. Then when you call it again, you add the 13 to the sorted array right here. And then what happens? So the 13, you swap the values with the 2. The 13 gets removed, so you now have 3 nodes. You would have a 2, a 7, and a 9. You swap with the larger of your 2 children, which would be the 9, and that's why you end up with 9 at the top, 2 on the right, and then the 7 is just where it was before. Call remove max again. This time we remove the 9. To do that, you swap with the rightmost node at the bottom. The 2 goes to the top, and then you swap the 2 and the 7 because they're out of order. You have the 7 and the 2. Call it again, and as you're doing this, you're adding the new elements to the sorted array. Notice it's sorting in descended order in this case. If it were a min heap, it would sort in ascending order. And call remove max again. So the 7 swaps with the 2. The 7 gets removed. The 2 is now the root, and it just happens to be the only node now. And then you call remove max again, and then 2 gets added to the array. So now we have a sorted array. It seems like a whole lot of extra work, but in fact, this is, in practice, very efficient. It's a very efficient data structure. In fact, this is the preferred way to implement priority queues. So if you ever hear about a priority queue, there's a multitude of ways to implement them. But the most efficient way, on average, is to implement them with the heap sort. Okay, if you implement it with, say a simple link chain or a simple array or different things like that, you end up with inefficiencies for either insertion or deletion, one way or the other. And if you want to maintain an average n log n, then it is good to use a heap to implement the priority queue. So that's why a lot of people, when you hear priority queue, some people just assume you mean also a heap implementation. Okay, so heap slightly slower in real world applications, but it's a very, very brilliant and ingenious way of doing it. It uses way less space than the others. So it is not stable, just like the quick sort, but merge sort is stable. And we see that the average time is n log n again, repeated extraction of max or min if it's min heap. Takeaways are that they are asymptotically optimal comparison sorts, so n log n. They differ in memory usage, stability, and practical speed. Quicksort is usually preferred in memory. Merge sort dominates in what we call external sorting. That's when you need to use, for example, part of the hard drive for very, very large data sets. That's very important in, say, big data applications like MapReduce. Heap sort is useful when deterministic, a big O of n log n behavior is required. Beyond comparison sorts. Okay, so beyond the comparison sorts, these are supposed to be planets, by the way, sorted in order. In reality, if they were that close to each other, it'd be very, very uncomfortable. Can sorting achieve linear time? So sorting algorithms can actually achieve linear time by exploiting numeric key structures rather than relying solely on comparisons. So the key idea is that comparison-based sorts are limited by n log n. That's the best they can do for their general limitations, right? But if we know about the keys, something special about the keys, integers within a fixed range, we can sort faster. These types of sorts can include counting sort, radix sort, and bucket sort. Common property is that they use key values as indices or digits, not pairwise comparisons. So counting sort, conceptually, what you do is you work, this works when keys are integers in a limited range from 0 up to some integer k, counts how many elements have each key, then computes running totals to determine positions. It's kind of a clever way to do it. Initialize a count from 0 to k array of zeros. For each key x in A, the array, every value in the array, you increment the count when you come across that key. Compute prefix sums so that the count at I equals a number less than or equal to I, and then place each element into its sorted position in output array B. So if you start with 4, 2, 2, 8, 3, 3, 1, all the keys are integers and they are between 1 and 8. So k equals 8. 8's the largest. So even though, for example, we don't use 0, we still make a slot for that. So you have slots from 0 up to 8. So it's in total, it's actually 9 slots. And every time you come across a specific value, you increment it at that position. So for example, the first value is 4. So we say count at 4. We look for 0, 1, 2, 3, 4, and you increment it. For 2, 0, 1, 2, increment that. So now you have a 1 there and a 1 there. I have another 2 in a row. So you increment that to 2. 8, You increment that, you end up with a 1 at the end. 3 and 3, do those in a row, you end up with two twos in a row there. And count 1, you end up with a 1 there. Okay. So next, you compute the running totals so that each position tells us how many elements are less than or equal to this position's value. So count at 1 is a 1, because there's only one element that has a 1 in it. Count at 2 is 1 plus 2. Okay, so that ends up being a 3. Okay, because remember, there's this, right? That's the count at 2. You end up with 3, because you've got these two. Count at 4, 5 plus 1. So count at 4, 0, 1, 2, 3, 4. That's the end value here. You have 6 there because it's 1, 2, 3, 4, 5, 6. Because you add everything equal to or smaller than it. And you have the same thing with count at 6. It's just, there's nothing there, so it's 0 plus the 6 preceding. 7, same thing, there were no 7s, so it's also a 6 because it's that or less. And then 8, there was one more element, so you have that. So now you have this new thing called the count array, or the cumulative count array. So it's 0, 1, 3, 5, 6, 6, 6, 6, 7. Then you build an output array B of the same length as the original array A using the counts. You then start subtracting the values to update the counts at the different positions. And you end up with the original values, but in a sorted order. It's very, very clever. It's kind of an interesting way to do it. You might have to sit and kind of think about it for a while. These are supposed to be minus equals. I don't know what happened here. Oops, that's kind of goofy. Let me see here. So these should actually be more like that, I suppose. Anyway, close enough. So I'm gonna go all OCD on you right now. Let's try to fix all these real quick so I don't go crazy. All right, let me see here. All right, you can watch, because I know it's fun for you to watch this. All right, Dr. Baugh fixes the slides live. Buy your tickets now. Okay, so you get the sorted values. Now, Radix sort is another clever way to sort without doing direct comparisons. So it sorts multi-digit numbers or strings by processing digits from either least significant or most significant digits using a stable subsort, often very similar to counting sort. So the idea would be that you kind of pretend there are buckets. So sometimes people call this bucket sort. They're really distinct, honestly, but radix sort, bucket sort is different. It goes by kind of more of a probability range or value range like that. But look at each of these values, and you look, for the first pass, you look at the ones that have, you sort them by their digits. So you're basically throwing them in a bucket based on their digits. So you've got a 0, so I put that one in the front. The next one, are there any 2s in the ones place? No. 3, 4, 5s. Yes, there is one with a 5, so I put 355 next. Is there one with a 6? Yes. So 436. One with a 5? Yes. One with a one with a, not a 6, with a 7 is what I meant. So it's 457 and 657. You do not consider the other numbers in here, just the fact that you met them in order. The 457 goes first, the next one, the 657, and then look for larger. So what about 29 or 9? I don't see any 8s, so let's go with 9. 329, any more 9s? Yes, 839. So there's my new pass 1 array. Pass 2, I look at the tens position. That's the middle position. So I look at here on this one and say, okay, are there any 0s in the middle position? No. Any 1s? No. 2s? Yes. Okay, well, that one stays there. What about 3s? Or, well, let's see if there's other 2s. Is there another 2? Yes, 329. So 329 gets put there. What about 3s? There's actually 2 of them, so 436 goes there, and then 839 goes there. What about 4s? No 4s. What about 5s? So 355 is one with a 5 in the 10th position, so we put that there. And then 457 goes there. And then finally, 657 is the third one. There's nothing with 6s, 7s, 8s, or 9s in the center position, the 10th position. The final pass is the third digit. Now we do it based on the most significant digit, in this case. So I put the, I look across all of these from the previous round, and I see which one has the smallest. Okay, any zeros? No. Any ones? No. Twos? No. Threes? Yes. So I put the 329 there. Any other threes? Yes. Next one in order I come across is 355. Any others? No. What about fours? So I start at the beginning again. Fours? Yes. 436 and then 457. 436, 457. What about fives in the hundreds place? No fives. What about sixes? Okay, let's go down the list. Last thing happens to be the one with the six. Put that there. No more sixes. What about seven? Well, the very first thing has a seven, so we put that there. No other sevens. What about eights? Yes, we've got 839. No nines. So we've got the whole thing now, and since we've just finished sorting on the last or the most significant digit, it's now sorted fully. And we never compared one element to the other. Okay, so it's a non-comparison based sort. Even though we're comparing the digits, if the number of digits was very large or it was bigger than the number of elements or something like that, that would make this not an efficient sort because you'd be doing more work than actually just using something like, quick sort or something. So analysis would be the time is big O of number of digits times the quantity n plus k, so number of elements plus the range of digits. So space is big O of n plus k. So number of values plus the range of digit values. It's stable, not in place. It escapes the big omega of n log n bound because comparisons are replaced by digit indexing, right? The next one that we look at is called bucket sort. And as I said, sometimes you might hear this mistakenly called as synonymous with Radix sort. They have some relations, but they are different. So concept is that it works for uniformly distributed continuous values in the range including 0 up to but not including 1. Divides the range into buckets. That's why it's called bucket sort. Distributes the elements, then sorts within each bucket. So often using insertion sort. And it is done in effectively one round instead of multiple rounds like Radix sort. Okay, so the number of buckets is usually proportional to n. It's either one bucket per element or slightly fewer. So for k buckets, arrays or list, for each element, x that is an element in A, place x in the appropriate bucket at floor of the k times x. Sort each bucket individually and concatenate all buckets in order. So for example, if I have this range right here, you could use numbers that are larger than 1, but this is just easy because it directly puts it in this 0 to 1 distribution. We could decide to distribute this since there are 1, 2, 3, 4, 5, 6, 7 elements. We'll decide to distribute it into, say, 5 buckets. Okay. Sort each small bucket. Okay, we see the ranges below. And then that sorting is typically just insertion sort. Okay, so it's a very simple insertion sort across a very small number of elements, so it's very efficient. So the bucket index 0 would cover the range, since we want to divide it into 5 equal ranged buckets. They're approximately 1/5 of the width each, so that's about 0.2. So 0.0 to 0.2 exclusive, 0.2 inclusive to 0.4 exclusive, 0.4 inclusive to 0.6, and so on. Okay, and then you just plop them into the correct bucket, and you end up sorting them within each, and you end up with a fully sorted array once it is, or data structure once it is spit back out. Expected big O of n if uniform distribution. The worst uniform distribution means they are more or less fairly spread. If you get a bunch of skewed elements, they're all very close to each other in the same range and none of the other ranges, you end up with n squared. So it does have a really bad worst case, but if you know it's over a uniform distribution, bucket sort can perform very, very quickly. Okay, space is big O of n, stable, but it's not in place. And then here's your summary of the comparison versus non-comparison, and it shows which ones are which and what to expect. Okay, application and broader impact. So these applications of sorting, the sorting isn't just academic. It underlines countless software systems. So where does it appear? Databases. It's used with query optimizers and indexes that use sorting for joins, grouping, and ordering results. Search and retrieval. So binary search we haven't covered searching fully, but binary search relies on it being sorted to begin with, otherwise it won't work. And data compression also relies on sorting. Graphics and gaming, depth sorting, also called such as the painter's algorithm, render order and collision checks, networking and OS, scheduling tasks, prioritizing packets and organization logs, AI and data science, sorting feature values for median, quantile, or top K operations are used. The bottom line is that sorting is the foundation of efficient organization and retrieval across domains. So why sorting matters, and beyond just sorting for the sake of sorting. So sorting is a microcosm of algorithmic design. So why does it matter for us as algorithm designers and analyzers? It showcases brute force, divide and conquer, greedy, and non-comparison paradigms. There's many sorts that we didn't even cover here, but these are kind of the primary ones. Performance principles are learned here, so asymptotic growth, data distribution, and cache behavior generalized to other domains. So searching, selection, hashing, machine learning. Sorting advances have influenced database engines, parallel computing, and external or disk-based algorithms. These were very, very important when we got to the point where large, especially big data applications with data science, that you just can't do the sorting all in memory because there's so much data. There's just not enough memory. There's enough secondary storage, for example, like with external devices, but there's just not enough memory, which is the RAM. So modern large-scale systems, for example, I mentioned earlier, MapReduce's shuffle and sort phase depend on efficient parallelizable sorting. All right, summary for this lecture, fairly simple here. Sorting unifies all major algorithm design patterns studied so far. We examined the elementary sorts, which are quadratic in nature, advanced sorts, which are linearithmic in nature, or linear logarithmic, n log n. We proved that the big omega of n log n lower bound using the decision tree model. I should probably say demonstrate. We didn't do like a thorough proof, but we explored non-comparison sorts, counting, radix, and bucket. They can break that bound, that n log n bound, by leveraging key structure over the comparison-based approach. Sorting demonstrates how theory meets practice. So asymptotic analysis, cache behavior, and data characteristics all influence real performance. We also learned that sorting illustrates algorithmic trade-offs. So time versus space versus stability versus simplicity, all of these can be impacted by what you choose to do. A lot of times there's going to be, one of the reasons bubble sort, Dr. Ellenbogen called it lazy student sort, is because it's very easy to implement. It's actually one of the easiest sorting algorithms to implement, but it's not good with efficiency. Okay, so it is simple, but it does not have very good time complexity. It's even among the quadratic algorithms, the elementary sorts, it's the worst performing typically. So it connects sorting connects mathematical lower bounds with practical system design. Techniques from sorting recur in many contexts: selection, searching, data structures, parallel processing. And in the next lecture, future lecture, we're going to shift from ordering data to retrieving it efficiently. So we're going to continue this theme of efficiency through structure. So keep your learning hats on and ready for that when that comes for the next lecture on searching. And then just a summary table here to see what the elementary, advanced, and then beyond the comparison sorting. So this kind of takes all the other tables, or most of the other tables, and then reduces it down to this. All right, so that's what I have for you this lecture. I hope that was useful for you, and I'll see you in the next lecture. Goodbye.